Okay, as promised, I wanted to make one video about differential equations. I'm gonna try to keep this limited to just one video. Um, so I want to introduce what is a differential equation, and we'll talk specifically about one very nice type of differential equation and solving that type. Um, so this is drawn from chapter 9. Offhand, I don't remember which sections of chapter 9, but it's just designed to give you a sense of the area called differential equations, because if you're in a science major, differential equations is a course you will likely need to take eventually. Um, so let's introduce them. So a differential equation is an equation. Shouldn't have erased the word, but differential equation is an equation whose unknown is a function involving one or more, so this is a separate clause, involving one or more derivatives. Okay. All right, so let me write one very simple example. So from calculus 1 even, we're familiar with problems that are basically equivalent to this. So we'd say like y prime equals, my marker's messing up, y prime equals, say, x to the fourth plus 2x. And so I can think of this as, this is an equation, and I want to know what is y. I know y prime equals x to the fourth plus x, but if I solve this for y as a function, of x, this problem just amounts to an antiderivative problem, or an integral problem. I'd integrate both sides and say y equals 1/5 x to the fifth plus x squared, and then put a plus c. So the solution, the general solution to this differential equation would be this function, this class of functions, this family of functions. Different values of c would give me different specific solutions to this differential equation. Okay, so this is a simple example of something that could be considered a differential equation. Another example that you've possibly seen before in calculus 1 would be an equation like this. P prime equals k times p, where p of t, so p is a function of a time variable t, is a population of some nation or some city in year t. So this is a population growth relationship, which says the rate of change of a population is proportional to the current population. Like if you have a larger population right now, it's growing at some percentage rate. So how fast it's growing in real terms is just a proportion. It's like 0.02 times the current population. Okay, so if I want to know what is the formula for the population function, that means I'm solving this equation for p, but as a function. I'm not algebraically solving for p, so I wouldn't just divide by k and say p equals p prime over k. That's not what we mean when we solve for a function. It means I need to come up with a formula for p in terms of the independent variable t, the input variable t. And you notice t doesn't even appear in this example of a differential equation. So I'm not going to show you how you solve this problem just yet, but a solution is of the form p of t equals we need a variable, say c e to the kt, where c is a constant. So let's just check that this is a solution. So something's a solution if it satisfies the differential equation. So what I need is, what is p prime? Well, this would be c, it's a constant multiplier, times e to the kt times the derivative of the exponent, which would be a k. So c times k times e to the kt, that is k times c e to the kt. But c e to the kt is my p function. So that's k times p. So p prime, if I follow the equations here, equalities, p prime equals k times p, so it's satisfying the differential equation. Right? So you may have seen that discussed in, I think it was chapter 3 sometime in Calculus 1. Okay, so I want to talk about I guess I should say one more thing before I talk about the specific. The order of a differential equation is the highest order derivative that appears. The highest derivative that appears in the equation. Okay, so both of the examples I showed you so far involve the first derivative of the function. But you could have a differential equation that involves the second derivative or the third derivative or some higher order derivative. So the order of the equation is the highest level derivative that appears. So if I have like y double prime and y prime in my equation, that would be a second order differential equation. Okay, so we're not going to be getting too deep in these. I'm going to be talking about just one specific type of equation. These are called separable equations. They're examples of a first order differential equation. Let me just start with an example. This is an example A. So let's say y prime equals x cubed over y squared. So this is a first order differential equation because the first derivative appears. That's the only derivative that appears. Okay. So basically, this equation is written so that I've already isolated the first derivative. The first derivative is by itself on one side. The other side is whatever else there is in the equation. When dealing with separable equations, and I haven't told you what a separable equation is yet, but when we're dealing with them, it's helpful to think of the derivative in the Leibniz notation, dy over dx. Separable means I can separate my equation into a side that involves y and a side that involves x. So in this case, I can multiply both sides by y squared and both sides by dx, and I get the equation y squared dy equals x cubed dx. So now I have this equation involving differentials. So a y expression times dy and an x expression times dx. So I've completely separated my variables onto either side. And then what I do next is integrate the sides of the equation. Integrate both sides of the equation. Excuse me. So that would give me 1/3 y cubed. I need to put a constant somewhere, but I'm going to have it on both sides. I'm just going to do it on one side of the equation. I'm just going to consolidate my constants on one side of the equation. So this equals 1/4 x to the 4th plus a constant c. All right, so after I've done that, after I've integrated, now the derivative stuff is gone. There's no y prime in this equation. So now, ideally, I'll be able to solve for y. I might not be able to solve for y depending on how complicated this stuff is. But in this case, I can solve this for y. Let's multiply by 3. We get y cubed equals 3/4 x to the 4th plus 3c. Now, as I go, let's just think about this constant. C, here in this equation, C could be anything, any number. Well, if I multiply it by 3, this 3C could still be any number. So rather than make things look more complicated than they need to, rather than calling it 3C, let's just call it K. I'll change the letter just to distinguish it from the previous constant. But K can still be anything. Now to solve for y, I just need to take the cube root. So y would equal the cube root of 3/4 x to the 4th plus my constant k. Plus got messed up. Right? So that's my answer for y. For this differential equation, that's the most general answer. So this is called the general solution. Okay, so it's a family of functions, a family of solutions. Any valid k there. Yeah, k can be anything for this example. Any number I pick for k, that gives me a specific function which satisfies this original differential equation. I guess technically I need to pick k so that I guess it'll yeah, that's fine. All right, so I've got the general solution. Let me keep it there for a minute. Now, another type of problem in differential equations is you have a differential equation together with some extra condition. So we could say y of 0 equals 4. This is called an initial value problem. So an initial value problem is a differential equation together with some value for the function. Given some x value, you have a specific y value associated to it. So that means we want a solution, a function that satisfies the equation that also satisfies the initial condition. So the way we handle this is, if we haven't already, we go through just like we did and try to find a general solution. And now we have a specific x-y pair. If x equals 0, y equals 4. So I'd take this equation and I'd set y equal to 4 and x equal to 0. and then solve for whatever constant is there. So that's 0, so 4 equals the cube root of k. So k is going to equal 4 cubed. So k equals 4 cubed is 4 times 60, yeah, 64. Momentary lapse there. So with k equals 64, that gives us not the general solution to the differential equation. It gives me the specific solution to the initial value problem. Y equals this function satisfies the differential equation and the given initial condition. All right. So let's define more specifically what a separable equation is. This would be an equation that can be written like this. dy over dx equals a function of x times a function of y. Where x and y are variables, but y is understood to be a function of x. But my equation can be factored like this. So in that case, we solve this, well, we separate this, I should say, by dividing by f of y and multiplying by dx. And then integrating. And then in the abstract, it's hard to follow, but we've got some expression that we integrate involving y. We have an expression involving x that we integrate. And after this, we get an equation involving y's and x's and a constant of integration plus c. And then we hope, in the best case, we hope that we can solve that resulting equation for y. If we can't, so sometimes after integrating, we get a complicated expression for y, and we're not able to algebraically solve for y. In that case, we have in some sense solved the differential equation, but it's only an implicit solution. It's the solution that describes a relationship between y and x, but as an equation, not as a function. This is similar to back with implicit differentiation in Calculus 1 in Chapter 3. But let's just do a couple other examples where that's not what happens. All right, so let's do a specific example here. All right, let's find the general solution to the equation dy over dx equals, we'll say y secant squared x. Okay, so that side of the equation is just a product of a y expression times an x expression. So we separate. We'll have 1 over y dy equals secant squared x dx. Then we integrate both sides. This will be ln of y. I guess you should be careful. Y could be positive or negative. We don't know, so we better put absolute values here. Ln of absolute value y equals tangent x plus a constant c. All right. So now we need to solve for y. So to cancel ln, I'll still have absolute value of y for a second. To cancel ln, I take e and I raise it to both sides of the equation. So I'll get e to the tan x plus c. That's in the exponent. So c C at this point could be any number. I want to solve for y. Right now I have absolute value y. Let's rewrite this. E to the tan x plus c. In the interest of space, let me just simplify it in my current equation. I'm going to split this up and write e to the c times e to the tan x. E to the c is a positive number, right? E to any power is always going to be positive. So right now I'm looking at the equation absolute value y equals a number k times e to the tan x, where I know k is some positive number because k was e to some power. But this is still absolute value y. When I have y and I take its absolute value, I get this. This is always positive. So if I forget the absolute value and just write y could equal plus or minus this. So we're getting every possible solution here. I could have positive k e to the tan x, or I could have negative k e to the tan x. But this plus or minus k, I could just think of that as a constant, as another constant. So if I continue replacing my letters, then I guess I could use L. So L, from what we've done so far, k was a positive number, plus or minus k then, which is what I'm calling L. It's just some non-zero number. So y is of the form L times e to the tan x, where L's some non-zero number. Okay. Let me erase some of this work. I want the equation as it originally appeared. So currently, it's looking like my solution has this form. Where L is some non-zero constant. But so that's almost a very nice formula, L times e tan x. But I've got this kind of artificial looking condition that L could be anything other than 0. What if L equaled 0? Then I would get the function y equals 0. So if L equals 0, my function would be y of x equals 0, the constant 0 function. And so let's check if that's a solution. It's not a solution that came from the work that I just erased. So if it's a solution, it didn't come from my work that I erased, but it looks like it should be a solution. So let's just check directly. Does this function satisfy the differential equation? Well, dy over dx, if y is the 0 function, its derivative is 0. And what is y secant squared x? That would be 0 secant squared x, which is 0. So dy over dx and this expression both equal 0, so they're equal to each other. So this is a solution. So my general solution to this differential equation, I don't have to exclude the case where L's 0. My general solution is every function of this form where L can be any number. Right? Okay, then if I had an initial condition, like if y of 0 is equal to something, then I could solve for what is L. just the equation, this is the complete description of all the solutions of this equation. Okay, so let's do one more. We'll do an initial value problem for this one. Suppose I have the equation dy over dx equals x squared e to the minus y. So there's my differential equation. Then I have the initial condition y of 0 equals 2. Let's solve this problem, this initial value problem. All right. So we start with by separating our equation into y on one side and x on the other side. I'm going to multiply by e to the y. Since it's e to the negative y, I multiply by e to the positive y to cancel that. We get e to the y dy equals x squared dx. So that's separated. Then we integrate. Integral of e to the y is e to the y. Integral of x squared is 1/3 x cubed plus our constant. Now, when I'm specifically dealing with an initial value problem, I can use, after I've integrated, after I've done this step, I can use my initial condition whenever I want to figure out what the constant is. And that may be less confusing than we saw in the last two examples where we kept that constant until the end and then figured out what it should be by using our initial condition. But what this is saying is when x equals 0, y equals 2. So I have an equation involving x and y that has to satisfy this condition. So if I plug in x equals 0, y has to equal 2. So I get the equation e squared equals 1/3 0 cubed plus c. I made a mistake in my notes. That's the issue. So e squared, y equals 2 and x equals 0. So e squared equals 0 plus c. So c equals e squared. Okay, so that tells me, I'm just going to erase and fill in the value here. That tells me I don't have to deal with this constant, this unknown constant c. I can just go ahead and plug in e squared for that constant. Our initial condition forces c to equal e squared. All right. So then y, to solve for y, we take the natural log of both sides. Y equals ln of let's think for a second. Is that good? Yeah. Yeah, that should be good. Yeah, just worried about absolute value here. Whatever this expression is, whatever x is, this has to end up being positive because e to the y is always positive. No matter what y is, e to the y is positive. So this is only going to be possible for certain x values, and that's going to be determine what the domain is for your y function. But I can treat this expression as a positive number because it's equal to e to the y, So when I take ln, I don't need to bother with absolute values, because this has to be positive. But then the domain of this function then will be only those x values which make this inside stuff positive. Right? So this is our solution to the initial value problem. Right. So that's the idea behind separable differential equations. This is a technique to solve these very specific type where the first derivative can be factored as a function of x times a function of y. That allows us to separate them to opposite sides of the equation and then integrate to get rid of the differential stuff, the dx and the dy. This is a very, very small subset of differential equations. So it's very easy to come up with equations that can't be separated. So this technique doesn't work. So in general, the topic of solving differential equations is a difficult topic. You have to study different types of equations and learn different techniques to approach them. And in general, if you make up a random equation involving derivatives of y, the y derivatives, it's very possible that there won't be a method that gets you to a formula for the function for y. So when you get into studying differential equations in depth, you also learn numerical methods for coming up with numerical approximations of functions. So like a model for the function, or a graph, an approximation for the graph of a function, that kind of thing. So in general, there isn't you're not guaranteed that there will be solutions to a differential equation, or that you'll have a method for finding a solution. But when you focus in on just specific, relatively easy types of differential equations, then there are methods for approaching them. So see separable here. This is enough for us. Like I've explained before, Chapter 9 is an optional chapter that we just cover if we have time. I'll put a list of a few problems from this stuff at the end of this video, just so you can attempt some and practice a little bit. We'll see if I'll make a decision on whether or not to include any of it on the test before I write it. My intent is for the test to be shorter than it would be normally, so I'm not eager to add more topics for the test. All right. So this will be the final lecture video for Calculus 2. If you have any questions about anything, let me know, and I'll figure out the best way of answering. All right.